Hello, and welcome to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the figures that count in the history of mathematics. I'm Benjamin Cornish, and today we're talking Hipparchus. Before we talk about Hipparchus, let me tell you a story. A few years ago, I was planning what I like to call my Around the World Ice Cream Conference tour. Yes, that's a real thing. I was mapping it all out on a flat world map, tracing flights from Naples for gelato, over to Tokyo for matcha soft serve, then New Zealand because someone told me they have pavlova flavoured ice cream. But here's the problem. I planned an entire 3-day symposium in Greenland because, on my map, Greenland looked like an absolute unit. A landmass so gigantic I thought, wow, they probably have their own 12 flavours of snow. Then I learned the truth. Greenland is not a frozen continent of dairy delights. It's kind of tiny compared to Africa. The map lied to me. Well, it didn't lie. It projected. And that's when I realised flattening a sphere into a rectangle messes with size, which means Hipparchus 2,000 years ago would have laughed at my itinerary. He was already wrestling with the same problem, how to turn a round world, or in his case, a round sky, into something flat without making Greenland look like the heavyweight champion of geography. That problem is at the heart of today's episode. Projections, measurements, and one Greek mathematician who figured out how to keep the cosmos on paper without stretching the truth. So buckle up and maybe grab an ice cream because Hipparchus was about to make maps, maths, and the universe a whole lot more accurate. The man who basically invented trigonometry, Hipparchus, while trying to look at stars. So, if you've ever stared up at the night sky and thought, I wonder what the cosine of Orion is, well, that's Hipparchus for you. He lived around 190 to 120 BCE, born in Nicaea of Council fame, and died in Rhodes of Colossus fame. And his own fame? Well, that revolves around his catalogue of the stars, the earliest surviving record, as well as his inventions, both physical and theoretical. And yes, he also invented a whole math subject, just because he needed it. Before we go knee-deep in sines and chords, let's set the stage. Hipparchus was born in Nicaea, which is in modern-day Turkey's north coast. This was during the Hellenistic period, a time when Greek culture had gone global, like Starbucks, but with more philosophy and fewer frappuccinos. Now, I've noticed that I say during the Hellenistic period for almost all of my episodes, but let me just clarify this a little, as it sounds as though every mathematician is Greek and part of the same nationality. You might be wondering at what stage in mathematical history the Greek nation arose as a political institution. And it was actually the same month and year that Charles Babbage received a grant of £9,000 from the British government to build the first computer. Now, this invention was a complete failure at the time, and it took many, many decades for anyone to take it seriously. The computer, I mean, not the Greek people. So yes, Hipparchus, just like many of our previous foci, was culturally Greek, but he belonged to the kingdom of Bithynia and escaped being our first Roman mathematician by about 130 years. Although he spent much of his life on Rhodes, which came under the Roman occupation when he was about 30 years old. So no, it's not all Greek to me. Unlike some of his predecessors, Hipparchus was quieter, more data-driven. His vibe? Spreadsheet warrior, before spreadsheets even existed. He wanted to know the position of celestial bodies with precision, and really, don't we all? Hipparchus didn't see maths as an abstract playground. He saw it as a practical toolkit. Where Archimedes might have built siege engines, Hipparchus built tables of trigonometric values. If you think that sounds boring, just remember, it is, and so do I. And unlike some mathematicians, Hipparchus did not live in isolation. He worked with Babylonian astronomical data, which he probably imported via something less convenient than a USB stick. He combined Greek geometry with Babylonian arithmetic, and that fusion is important because it shows that mathematics is rarely a solo act, it's a band, and Hipparchus played lead trigonometry. In fact, Hipparchus's trig tables were so high quality that they didn't survive today, but what we do have is Hipparchus's work with his name scribbled out and Ptolemy's written instead. And all the numbers changed just a little to make it look like original work. To appreciate Hipparchus, let's quickly recap what came before. Earlier thinkers like Aristarchus had proposed heliocentrism, which everyone politely ignored for about 1800 years. Others mapped stars and constellations but didn't quite measure them systematically. Hipparchus stepped in and said, let's stop eyeballing it and start quantifying it. He invented rigorous measurements, comparing observations over time. He wasn't just asking where the stars were, he asked how they moved, and that led to one of his biggest contributions, discovering the precession of the equinoxes. And what's that? Well, precession is the slow wobble of Earth's axis, like a spinning top that's had one too many espressos. It means that over about 26,000 years, the position of the equinoxes shifts around the zodiac. Hipparchus noticed that old star charts didn't match his observations. That's like noticing your GPS is off by a city block because Earth is tipsy. And for those of you at the back who didn't do the reading for today's class, the equinox is the date when the sun crosses the celestial equator, which means that the day and night are of equal length. This should happen twice a year if all goes well. Now, let's talk trig. You can't do serious astronomy with pure geometry, it gets clunky. Hipparchus needed a way to relate angles to lengths in a circle efficiently. Enter trigonometry. But before you start picturing sines and cosines, hold up. Hipparchus didn't use them. He used chords. Imagine a circle, draw an angle at the centre. The chord is the straight line connecting the 2 points at the circumference that define the angle. If you know the chord length for a given angle, you basically have what today we would call the sine functions. Hipparchus constructed a table of chords for angles from 0 to 180 degrees in increments of 7.5 degrees. That's 24 values, which was enough for the interpolation. His circle had a radius of 3,438 units. And why 3,438? Well, we notice that is 60 times 57.3, and 57.3, you might notice, is the number of degrees in 1 radian. Ah, yes, Hipparchus was thinking in radians, without the concept even being formalized yet. Citation needed. The formula he effectively worked with is what we now know as a chord of theta is equal to 2r sine of theta over 2. And in his case, r is 3,438. And this is not really any more archaic than what we do today. Now, yes, you have your sin button on the calculator, but all it is really doing is looking up a value from a memory table and interpolating between 2 stored data points, or possibly using a Taylor expansion, depending on the model. Here's something you might not know. Hipparchus also gave us the first comprehensive star catalogue in the Western world. About 850 stars, each with coordinates. He basically said, look, if we're going to navigate, predict eclipses and impress people at dinner parties, we need a database. He also devised methods to predict solar and lunar eclipses more accurately than anyone before him. And he invented, or at least significantly refined, the concept of geographic coordinates, latitude and longitude. Yes, those are the same systems that your Uber driver misses today. They started with Hipparchus. Granted, his were not as simple as lat long. He used a combination of elliptical coordinates and equatorial coordinates, but let us not split hairs. But perhaps the most impressive, his star chart included a new star that was not known to people by previous sources. Hipparchus claimed that this new star emerged during his lifetime, which might be the first account of a supernova, beyond one allegedly drawn in an Indian cave painting. However, his supernova was not preserved in the historical record with sufficient confidence to put it on the Wikipedia list of historic novae. I will count it here with no citation sought. Let's give Hipparchus some credit for being hands-on. He wasn't just crunching numbers, he was also building gadgets. Because when your research needs data and no one's selling telescopes on Amazon, you make your own tools. One of his most notable creations was the astrolabe, or at least an early version of it. Think of the astrolabe as the Swiss Army knife of ancient astronomy. It let you measure the altitude of celestial objects, figure out the time, and even solve spherical geometry problems. Hipparchus didn't leave an instruction manual, but later sources attribute its development to him. Then there's the dioptra, a kind of ancient surveying instrument. Imagine a telescope without lenses, mounted on a rotating axis with a graduated circle. Hipparchus used it to measure the angular distance between stars. He also developed instruments for determining geographic latitude. Remember that coordinate system he introduced? He needed tools to make it real. By measuring the altitude of the sun at noon, he could pin down a city's latitude. It's basically the ancient version of share my location, minus the part where your friends ignore my texts. And we can't forget the amiliary sphere, a skeletal globe showing the celestial circles, the equator, the ecliptic, the tropics, all represented as brass rings. With it, you could model the heavens in 3D, which, let's be honest, is way cooler than when I do it in a 2D PowerPoint. Hipparchus didn't just innovate for fun. Every invention solved a data problem. He wanted accuracy, and he built the hardware to make it happen. In a sense, he was an early engineer, but also a hero of modern mathematicians who still butt heads with seemingly impossible problems that they realise they need to invent something new to solve. Okay, so picture this. You're Hipparchus, you've catalogued hundreds of stars, and now you want a star map. One problem, the night sky is curved, really curved, like Earth is round, sorry flat earthers, curved. How do you turn that into a flat map? Well, enter spherical projection. I wouldn't want to sound too biased, but this is easily my favourite projection. A spherical projection is a way to represent points from a sphere onto a flat surface. Modern cartographers wrestle with this all the time because you can't flatten a sphere without stretching or squashing something. That's why Greenland looks like it's trying to be the continent on Mercator maps. Hipparchus proposed the stereographic projection, a specific type of spherical projection where you imagine a light source at one pole of the sphere projecting points onto a plane touching the other pole. The result? Circles on the sphere, like latitude circles, become circles on the plane. Angles are preserved too, which is very handy for astronomers. So why did Hipparchus care? Well, it's because he wanted accurate star charts. By projecting the celestial sphere onto a plane, he could plot stars on a flat surface whilst maintaining angular relationships. It's like taking a selfie of the sky, only with maths, ink and papyrus, instead of a long exposure camera. Fast forward to today, stereographic projection is still used in geology, optics, and even virtual reality systems. Every time you use a panoramic image, thank Hipparchus. Talk about flattening the curve. Now, let's inject a little personality. Hipparchus had opinions, strong ones. For example, he disagreed with the idea of a perfect celestial sphere because his data said otherwise. In other words, he wasn't afraid to say, actually, at every ancient Greek cocktail party. I should note that this celestial sphere is the one on which the stars are painted, not the one that we stand on. Although interestingly, we do not stand on a sphere, but rather an oblate spheroid, which is the fancy way of saying the Earth is flat. Again, citation needed. He also worked with Babylonian arithmetic methods, which must have made his fellow Greeks raise an eyebrow, but he didn't care. He was too busy being correct, and maybe too busy thinking up new ways to measure things. Hipparchus wasn't universally adored. Some thought he overcomplicated things. Others disliked that he leaned on Babylonian data, and centuries later, Ptolemy got most of the glory for Hipparchus's developed ideas. A classic case of group project, one guy does the work, the other guy gets the grade. So why does Hipparchus matter? Because he showed that maths isn't just abstract, it's a practical tool to decode reality. His methods shaped navigation, astronomy, geography, and eventually physics. Without him, Columbus might have gotten even more lost, and your phone might not know where the nearest coffee shop is. He didn't just look at the stars, he gave us a way to measure them, predict their behaviour, and indirectly understand our place in the universe. And along the way, he basically said, if you can't measure it, you can't know it. So next time you look up at the night sky, think about Hipparchus with his handmade instruments, scribbling down star positions by lamplight. No telescopes, no computers, no apps, just a sharp mind and the determination to make sense of the cosmos. And remember, he gave us trigonometry. So next time you're struggling with a sine wave, whisper a quiet, "Thank you, Hipparchus," or maybe "Curse you, Hipparchus," depending on your grades. And that's it for today on the Mathematicians Podcast. Please comment on the episode or give it a thumbs up, share it with a collection of 50 to 60 friends, or find my personal home address on the dark web and send me a box of gold ingots. It really does help the podcast. If you can't wait for me next week, then you can connect with me on Blue Sky at mathematicians-pod or YouTube at un-applied maths. Next week, well, before we reach next week, I need to read through my list of the 100,000 historical mathematicians to decide who gets an episode. But we're coming into a rare time for maths, so I shall give an honourable mention to a few people spanning 200 years who were mathematicians but did not contribute more than a paragraph or two to the body of knowledge. Zenodorus, Posidonius, Marcus Terentius Varro, Zeno of Sidon, Geminus of Rhodes, Cleomedes, Theodosius of Tripoli, Pamphila, born around 60 CE, is the first female name on my list of mathematicians, and I am devastated to be skipping her, but I just cannot find any of the maths that she did, nor do I really know why she's on the list that I'm using. But sadly, the suppression of female works has been a common thread throughout history, and she may well be our first casualty, or at least the first casualty whose name I know. I should say, much of her work on history does survive. You should go look it up. She wrote a list of 14 famous women in war. It's just not the maths. So, fast forwarding 200 years, next week we meet the hero of maths. Well, the hero of Alexandria, our first Common Era mathematician, our first Roman, our first so many things. So let's talk Stork Heron of Alexandria next week on the Mathematicians Podcast. Until then, goodbye. The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.